Okay, let's get started. So today, okay. All right. So today we're going to talk about light and color. So first of all, basically it's a basic component of basically we're looking at one particular pixels. Okay. So there are even with this simple, we will reveal that there's actually we'll talk about two applications coming from these simple principles. So first of all, let's look at what the image looks like. Okay, so this is an image. It's a little bit too high resolution, so we don't see what's going on. So let's downsample it a little bit. So these are kind of if you kind of downsample this sufficiently, you can see that okay, an image is basically a 2D array of these kind of elements, and this is called picture elements. So it's called pixels. Okay, so and if you look at these pixels, and you can see this is a grayscale image. It's just 2D array of pixels. And then you can have if you just look at each of them, what's in the representation of the computer, it looks like this. So here I'm overlaying the pixel intensity. Basically, it's an 8-bit representation, so that it represents the number between 0 to 255. Okay, and so this range, if it's larger, then it's a brighter pixel, and if it's lower, it's a darker pixel, right? So you can see here you only have 26, 25. And where you have a brighter region, you have around 236, 32. Okay. Okay, so this is how you kind of represent from the computer's perspective. This is how you represent an image, but we have color images, right? How do you represent that? So as you may know, the computers represent the color through RGB channels. And these channels basically can represent by this, right? So you have one image that's a R, the red image, and a green image, and a blue image. And you can actually separate them into these 3 channels. So they have 3 channels that basically specify how much light, how much red light, how much green light, how much blue light you should, the display should emit so that you see the particular color. Okay? So that's basically it. But what we really want to know is like, where do that pixel intensity, where those numbers come from? Okay, so we want to talk a little bit about that. So in order to understand this, we need to understand how the images form. So you have this light source. Maybe this is a light source that's outside, or it's a light source that's indoor. And light source will emit light rays, and the light rays will be hit by some surface area, for example, the tabletop, the wall, or our skins, and that surface, it will scatter those light. They'll reflect. The light will get kind of bounce from the surface. They will be kind of scattered through the environment, and some of the lights will be kind of captured by an imaging system. And then you will get a pixel intensity there. Okay, so basically you have taken two main processes, right? So to determine whether a pixel has certain intensity, you have 2 properties, right? One is how the surface reflects light, and how the light get measured by an imaging system. That's your camera. Okay, so this is a high-level overview. So let's first talk about how light bounces off surface, and then we will try to see if we can build a application from that knowledge. Okay, and then we'll do the same for imaging system. Okay, so let's talk about light bounce off surface. The simplest surface of this kind of refractions, how light bounce off the surface, is something the surface is very shiny. Okay, what is the things that are very shiny? Mirrors, exactly. So you have a mirror. So imagine that you have a person here, and then you have a mirror image here. Okay, it's very, very simple. So what a mirror looks like is the following. So if you have a mirror, and then you have so this is the center is a mirror, and then you have an object here on the left-hand side, and what you see is that if you are this is a person, if you look at the mirror, okay, what you see is that whatever light ray that's kind of the environment has some light ray, and light ray bounce off these persons, and then you will kind of light ray coming from here bounce off. And the way the mirror, if it's a planar mirror, basically it's just a horizontal, just a single plane, the light ray will bounce off through this angle. Okay. Quiz this physics quiz. What is that property called? Law of refractions. Okay, right. So basically, you will bounce off the incident angle, and the refraction angle will be the same. Okay. So and then if you have different light ray coming off here, and then you will bounce through this way. All right. So the interesting thing is that all these, if you have planar refractions, all these light rays will converge on the other side. Okay. This is why it will, if you are a person somewhere here on the left-hand side, if you look at the mirror, what you'll feel is that there seems to be someone on the other side. Okay. And if you look at from this one, it feels like is someone on the other side and emit light rate like this. Okay. And this is called a virtual image. All right. All right. So
look at this.
So it kind of creates confusions.
Know that that's.
So I'm not sure whether you have seen this before. Basically, people get freaked out that that somehow the
look at this. How does the mirror know that that's?
So people don't know about how the refraction works, and therefore they feel very weird that the mirror knows there's I don't know what that is. It's a kind of yoga or something. How that things knows is there, right? Even though it's kind of block these things. Okay, let's see if you can show this. All right, so here's a occluder. So you have a occluder here, and you have an object here, right? So this is the object here. And the key idea is that how the mirror knows, right? The mirror doesn't know anything, it's just reflecting light. But the thing is that the object will reflect light rays from all directions. So for example, if the object reflects light rate, like there's some light bounce off from this object surface, and once they bounce off from this surface, you can look at the surface normal, like this is surface normal, and they reflect light ray like this. And the idea is that all these light rays will converge on the other side because it's a planar mirror, so it converges on the other side. So you have a virtual image here. Okay, so when you look at this mirror from this angle, then you see the objects from the other side. Okay, as if the mirror does not exist, right? So there's a virtual image there. And this is why, even though it doesn't matter whether you have an occluder here, you will see the mirror here. Okay. So next time, if you see that TikTok video, you will be able to debunk. You will be able to explain why you see why the mirror knows the object is there, even though you have an occluder. Okay. All right. So it's kind of a bit boring that like why is this important? Like why is this useful? Okay. So for example, here it's you have like this can generalize to anything, right? For example, this is a planar beam mirror, but if you have something weird shape, then you will be able to see. You follow the same principle. Like when you have a light rate, you have a directions, and if you know the surface, if you know the surface orientation, that's you know the surface normal. Like here is the surface normal, and then you will be able to know where the light bounce off. Okay, where the light bounce off. So this a prime example is the beam in Chicago. All right, in Chicago they have this beam, and then you can see that how they warp the surrounding inside that mirror. Okay. All right. So can this be useful for computer vision? So in my own research, I did this before. So basically the idea is that if you have a person and you know their light cornea, that the cornea actually the cornea is these regions. The cornea actually reflect light, so it's like act like a mirror. And the interesting thing is that no matter your race, your gender, no matter your age, your cornea size, the geometry is the same. All right, that's something unique about human. You don't actually grow your cornea, your eye, get larger as you grow old. And by the way, that's why the kids, kind of babies, are cute, because their eyes are the same size, but they're tiny. All right, so because the cornea reflect light, and we know exactly what your cornea shape is, and therefore, if I know the size of this circle, then I will be able to know what the 3D geometry of that kind of. You can think about there's a mirror in the sky in the space, and for that we can use this signal to cast light rays from this light ray and hit the cornea, and then they will reflect light. And therefore, you are able to use this to reconstruct, like do 3D reconstructions of the thing that you did not see immediately. Okay, you can recover the 3D-dimensional shape of the thing. Okay, so this is how kind of simple application of this light refractions. Okay, so here's another example. It's a synthetic example where you have an eye, but you put it in a virtual environment. If you just look at the eye, you are able to recover what environment the person is in. Okay. All right. So, by the way, so if I'm moving too fast, or if there are some questions, please feel free to kind of interrupt me and then ask questions. I'm happy to kind of like answer questions. All right. Okay, so but so far it's very easy. Like just the mirror reflection and everything is easy. But the thing is that it's not like the real, like whenever you look at the different surface, it's not just like a mirror, simple mirror refraction, right? So for example, you have like your reflection. If you have a ball here, like for example this guy, it's not entire mirror refractions. So you have something you will reflect, but you will based on a surface normal, a part of them will actually refract according to this if it is a shiny surface, but many of them they will scatter a little bit because the geometry there is not perfectly smooth, and therefore some of the light will bounce in different directions, and therefore you typically see something like this. Okay. Right. So how do you kind of, so you essentially have like light ray like this, and then you have a lighting directions. It's a vector that specifies the lighting directions, and you have a surface normal. That's a surface normal like this, and your refraction angle like this. All right. So one way to and then you have an observed location like this. Okay. So basically, how you can that we can characterize these refractions by using some simple math. All right. So this is once you specify these angles. All right. So you have this angle. Basically, you want to see how much light you will see from that viewing angle if this surface has certain refraction models. All right. So we know that this is the refraction orientation. This is the R is the refraction orientations. And then you can see that, okay, so if the viewing direction at exactly, if the theta, if the phi angle is 0, then it means that it will receive the most amount of light, right? If this is a peak there, it will have receive most amount of light. If the phi is small, is large, then you will see, ideally what you will want to characterize is that the light gets dark, less light, right? You get darker, okay? So how do you characterize this? So essentially, one way to do this is that the viewing direction, the light you receive from that is the in source light source times the cosine phi, right? So cosine phi has this property that if the phi is small, then it's close to 1. If phi is large, then it's close to 0. Okay? Does it make sense? So what do I want to what I want to characterize is this behavior. Okay? So I have a refraction, I have a surface, I want to characterize this refraction behavior so that I can use this for modeling and so on. So one way to characterize this refraction behavior is that I want some mathematical equation that tells me if the viewing angle is directly at the refraction angle, then it will be the maximum. And if it's deviated, it will be smaller. And one mathematical kind of characterization is taking the cosine phi. Okay? All right, but I don't want to kind of just write down the cosine phi. I don't want to introduce another variable like a phi. So can anyone tell me what the because this is the direction, this is the viewing directions and refraction direction. Direction means that I only tell you the directions. I don't need to tell you the what length, right? So basically the unit vector, right? So they're unit vector. So can anyone tell me that if I have two unit vector and the angle cosine phi between them, how can I compute that? If I have a two vector, okay, so this is high school math. You have a two vector, and I want to and then there's some include angle between that vectors, like phi. What is the cosine phi? If I give you two vectors, and they're unit vectors. Yes? Yes. So it's the answer is the dot product. If I have the dot product between R and V divided by the length, right? So I think it's called the law of cosine. I don't know what but basically you should learn this in high school. And the thing is that because the refraction direction and the viewing direction, they are unit vector, so you don't need to divide it by the norm. They're one, and therefore you can clarify this is the you basically you can compute cosine phi by just taking a dot product between these two vectors. These two vectors are three-dimensional vectors that in the space. Okay. All right, so it looks like this. So if I have a ball and it looks like this, okay? So if I move, okay, so this looks like this, but you can then categorize like how shiny like the material is by saying that if this is kind of less shiny, right? They are kind of less shiny. I can categorize how shiny they are by raise the power of this guy, right? If the power is 10, then it has one spot there. Okay. And this is called and then by the way, so because the dot product could be negative, right? So because cosine phi could be negative if the angle is that, but you don't have the notion of negative light, right? So therefore you will need to use a max to make sure that they cap at lower bound 0. Okay, and there's a name for this refraction model. It's called foam refractions. So this refraction model basically helps you to simplify how light bounces off the object surface, right? Something that's shiny. Yes. I know 0 to 2 different times. So if you have some light source that's, for example, if your viewing angle and the refraction angle is larger than 90 degree, then your cosine phi is like larger than 180 degree. The cosine phi become negative, but you actually don't receive any light you don't see that any refraction there, but the math tells you they receive negative. Okay, you don't see it. Yeah, you don't even see it. Yes.
For this particular foam reflection equation, is to the power of 10 needed, or could it be any number?
Yeah, it's a hyperparameter, right? So for example, if I'm a graphics designer, I need to design my object material. And this is a very popular one. Like I can decide, okay, how shiny this object is, like this surface is, by specifying, okay, maybe I want to be more shiny, then I can increase the numbers there. Yes. IL is also so IL is this I think it's here it's a scalar, right? How bright is things. Okay. Okay, so you can further, so this is full interaction. If you move this light source around, this is what you'll see in this object material. Okay. All right, so some people can, you can further refine this refraction model by saying that, okay, this is kind of doesn't look very realistic. So what you can do is that you can kind of refine this by saying that, okay, based on the light directions and the viewing direction, you have a halfway vector. And instead of computing the cosine theta between the refraction angle and this and the viewing direction, you use the halfway vector. Okay, and this is called Bing-Fong refraction model. So this will look make sure that the refraction looks more natural. Okay, so you can see it looks more symmetric. So let's see the comparisons. Okay. So on the right-hand side, it looks more natural. Like, so this is just a different way of characterizing a refraction model. All right. So, and these things is kind of everywhere. Everything you see has a part of refracted components, like this kind here, this ball here, and this kind of coins here. They have some of them that are refracted, and some of them are diffuse. But there's some material, they are fully diffuse. What does that mean? It's kind of like these materials, right? These are fully diffuse, means that maybe my t-shirt or something that's the idea is that because the surface area, the surface geometry is very rough, and basically whenever light comes in, it just diffuses to every directions equally. Okay, it will look like this. And the interesting part about this model is that this kind of material is that no matter where you look at that surface point, you look the same, right? If you have something shiny, then if you change your viewpoint, look at that something shiny, you see a very different appearance, right? But for diffuse material, no matter where you go, it looks similar. Okay. And there's a reason why they look similar, because the amount of light they receive and the amount of light they reflect, they cancel out. Okay, so they cancel out so that they have the same amount of light received from everywhere. Okay, so this is probably not that important. Okay, so but that doesn't mean, okay, so we said that the amount of light we see refracted, they reflect everywhere, and therefore you see if they're at the same location, and you see every location you see from different viewpoints, you see the same color, the same intensity. But that doesn't mean that the same material will behave differently if you have light is. Then the question is, why here this brighter here, the kind of this brighter color, and this darker color here, right? So it depends on the light's orientation, the orientation between the surface normal and the lighting directions. So this is a very important property that we'll use many times. Okay, so why is that happening? So imagine that you have a beam of light, and a beam of light that hit the surface. Okay, so these are beam of light hit the surface, and this surface is this type of surface called diffuse surface or numbersion. There's some term for that, but these lights get refracted this way. Okay, all right. So this beam of light has a surface area like these guys. Okay. But now imagine that the light is coming not from directly on the surface orientation, but from an angle. Okay. Imagine that the light is coming from an angle. So now can anyone tell me, is this area smaller or larger than this area? Any idea? Yes, larger, right? Because the same beam of light, the same amount of light, they get kind of distributed into a larger area, which means that these area will receive less light. Per area, receive less light. Okay, so you see less light. And the amount of light it receives, you can do some simple calculations that it depends on the cosine theta between the lighting direction and the surface normal. If the theta is large, then you see less and less light. If theta is small, like in this case, theta is 0, then you see the maximum amount of refractions. Okay? So it looks like this. So you can kind of model this behavior by saying that the output light you see from any directions depends equals to the input lighting strength times the cosine theta. The theta is between the lighting direction and the surface normal. All right, so it sounds like it's just a random equation, but why do we care about this? Right, so let's see, and by the way, so these things similar than the refraction model before, I can model the cosine theta, I can compute the cosine theta by taking the direction of the lights and the direction of light and the surface normal. All right, so I can take this dot product. And also because we don't see negative light, there's no such thing as negative light. So, but dot product can be negative, and therefore you need to cap this at 0. Okay. All right. So there's another thing that's we haven't modeled yet. That is like how much light that will be absorbed by the surface. For example, I'm wearing a darker t-shirt, right? And I will, in this case, the t-shirts will absorb more light compared if I wear a lighter color t-shirt. The lighter color t-shirt will reflect more light, and that property, how much light the material absorb, is called albedo. Like basically, you can think about this specify how dark that surface is. Okay, so with this, you can show the example like this. It will look like this, right? So if you have a light source from here, and you will see the ball like this color. So this will be dark because they never receive any light. You will see that it's kind of very diffuse color that match this kind of the notion. All right, so you will look at this. If you move light source around, you will look at this. All right, so I promise that I really want to motivate this, like why you want to learn, why you want to learn these things. So here is a practical example. Okay, so imagine that I have an object. I want to determine the 3D shape. I want to know the 3D shape of that object, but my camera is fixed. I don't have this multi-view, like a stereo information about the 3D shape. I just have one camera. Okay, so how do I determine the 3D shape of the objects? All right, so assuming that the object is non-Gaussian, and most of the objects are like my face, and they are pretty diffuse. Okay, so it will look like the following. So here you have a lighting directions like this, and imagine that you take a picture from this angle. Take a picture from this angle, and you take this picture, and this is a ball, so it looks like this, right? So imagine that this is what happened. Okay, you take a picture like this. Okay, and now what you do is that you move the light source. You change the light source direction. So imagine that you have a light source that you can change. You change your light, and then before you change your light source, from that perspective, you capture image 1 basically for every pixel, you record the intensity of that pixel, okay? And then that image one intensity is the albedo that you don't know, and times the dot product between the lighting direction and the surface normal. Okay. All right. So this is the equation, right? Equation. But I couldn't really solve this because it's only one equations. So I don't know because they're all entangled, right? I want to know what the albedo is. I want to know what the surface normal is. Okay. So that I can reconstruct the three-dimensional shape of the object. All right. So what we do is that let's just capture another image, right? The camera doesn't move, but I move the light source. I now have new light source. I change the light source directions and I capture another image. Okay, there's I2 now, and I do the same thing for I3. Okay, I capture another image. So by these three images, I will now have everything I need to recover the 3D reconstruction. Okay, so let's see how we can do this. Right, so by this simple modeling, right? So here's what it looks like. So now you have these three equations, right? It's not clear like how things will work. So let's move these three equations here. Okay, these are the three equations. And then what we will do is that this equation basically is valid for every single pixel. Okay, for every single pixel, you have this pixel's intensity I1 and equals to the rho of this. N is the surface normal of that pixel. Okay, so what you'll do is the following. So you know these three equations, and what you want to get is the following. What you're going to get is the albedo, basically how much light it absorb or reflect the reflect light, and the surface normal, like what's the orientation of that surface. Okay, so you want to do this, and what you can do is that because now you have three equations for one pixel, right? For every pixel, you have its own equations, a set of equations. So here is where your linear algebra knowledge comes in. So now you have three equations. So in order to solve a linear system of equations, what we need to do is to write them down as a linear system equation in terms of matrix form. And then we can solve the linear least square. Okay? So how do I do that? So I know that these three equations, and I just concatenate this three into this. Okay? I just concatenate the three is a vector. Now the I1, I2, I3 is a vector, and L1, L2, L3 transpose, they are, because L is a three-dimensional vector, so L1 transpose is a row vector. Okay, so here this is a 3x3 matrix. Okay, it's 3x3 matrix, and then the rho and n, rho is a scalar, right? It's basically how much light it reflects. It's between 0 and 1, and the surface normal is a vector. Okay, it's a column vector. So here you have a linear system of equations, and on the left-hand side, this is something you know. All right, and then this matrix is something you know, and on the right-hand side, this rho times n is something you don't know. Okay. So what does this look like? It looks like AX equal B, right? So it's a linear system of equations, and you can solve this with linear algebra, with this square. Okay? Yes?
Why do you need three observations? Couldn't you do it with two if there's only two unknown variables?
Yeah, that's a good question. So you need three here because surface normal, you need to ambiguate the surface normal. Surface normal have a three-dimensional components, even though they have only 2 degrees of freedom, but because you also have the rho, you need 3 observations in order to solve this linear system of equations. Remember that if you have 3 unknowns, and you need 3 equations to really solve that. right? Otherwise, you will have infinite number of solutions. Okay? Does it make sense? Make sense?
So what are the two axes we need for the surface?
The-
Right, since you're saying that there's 3 dimensions of it and we don't know 2 of them, is that what you're saying?
They have 3 numbers that you don't know, but you have a constraint that is a surface normal. This n vector is unit norm. So you only need 2 degrees of freedoms. But you also need to determine the rho, and therefore you need 3. Okay, so you have 3 unknown, 3 things that can move. You need 3 equations to really solve it. There's also a kind of nuance here, which means that if you think about this linear system equation, this is 3x3 matrix, which means that this 3x3 matrix must be invertible. Okay, which specify that your light source cannot be linearly dependent. You cannot have a light source that leads on a plane, and that will lead to degenerate solutions. Okay. Yes.
If you use more than 3 pictures, would it give you a more accurate?
Exactly. Yeah, you will get more accurate. Basically, you just add more rows in this linear system equation. Maybe you have 20 light source, and then you have a 20 light source, but you still solve the same thing. This unknown doesn't change. You have the same amount of unknown, but you get more observation, like because you have more like 20 observations, and you have 20 light source directions, and you can solve for it will become this linear system will become over deterministic, and then you can solve for least square solution. All right, so it become more accurate. Yes.
I can think of a lot of cases where you have fixed light source. Could you also do this by moving the camera around and keeping the light source and object fixed?
It will be a different application. Like later on we'll talk about that if you have a moving camera and you can recover the technique is different. Like when you have a moving camera and your object doesn't change, that corresponds to you can if you find a correspondence between the images, then you can triangulate where that object is fixed, right? So that is a kind of multi-view reconstruction. So here, this type of technique is called photometric stereo. That is, they can do the stereo, but without moving the camera. That they can recover the 3-dimensional geometry without moving the camera. This is a single view. Okay. Of course, you can combine this with other things as well. You can also move the camera, multiple light source, and so on. Okay. All right. So let's see how we can solve this. So let's kind of call these vector as I and sorry. This I and this L is a 3x3 matrix. It's a big L, and let's group this rho and n together. So let's call it G, and this G. Then you can solve for G, right? So you have linear system equation. Then you can solve for G by taking the inverse of this guy. Okay, so you get a G. All right, but we don't want G, right? What we want is a surface normal and albedo. How can I do that? How can I factor this out? Any idea? Yes.
Does the surface normal have to be a unit vector so you can make sure you take out whatever the magnitude is?
Yes, exactly. So you know G, and because they are unit vector, and therefore G is the albedo is just the magnitude of G. Okay, and you can get the surface normal by taking the G and divided by the albedo, and that's your surface normal. Okay. All right. So what does that look like in the actual case? Is that just a ball? You can take a person's. Sorry. Yes. Oh, by the way, all the slides are online. Yeah. All right. Okay, so let's look at this, right? So you have an observed intensity. So imagine that you have a person sitting there. You capture multiple photos of this. Then what through the process. So for every, you'll repeat the same solving the linear square equation for every single pixel. Okay, and now here is like it's very simple, right? For every single pixel, you observe multiple observations. Imagine that you have 20 observations, and what you get is going to be a 20 by 1 vector equals to a 20 by 3 matrix. That's a light directions, and solve for a 3 by 1 vector for every pixel. And what you get is that you can recover the albedo of this person, and you can also recover the shape of this person, like what the surface normal of this person looks like. And if you can do that, you can recover the albedo texture map. Okay, you can 3D reconstruct this person. Okay, yes. Yes. For every single pixel, you solve that tiny linear system of equations.
So you recently put like 3 different or like 3 or more light for every single.
Yeah, exactly. So because I think I want to talk about this because this capture a lot of like computer vision algorithms. Basically, what you know is that you have a full model that describe how you observe what's the fundamental physics behind what you observe and what you don't know, the physical property, for example, surface normal and the albedo. Okay, and and then you have a mass model to describe this, right? This is the intensity is just the albedo times the dot product between these two things, and with that, if you capture multiple observations, you just set up the linear system equations, and you can solve the unknown. Okay, you can use your camera you can recover something that you didn't directly measure. Okay, and that's basically the computer vision is about. All right, so where do we see this type of application? We showed this last time, right?
We're here at the White House working with the Smithsonian Institution.
So we show that
creating a 3D presidential portrait.
similar.
And
that
the system that we've launched
some
as
probably
part of this
more
process,
advanced,
it's called our mobile light stage.
but what they do is very similar.
Inspiration
Okay.
for the project of creating a 3D portrait poked with a sitting here instead.
Relatively quickly, we will invite the president to
So
sit
they have
down.
multiple light
He will
sources.
be surrounded in front by 50 custom-built LED lights, 8 high-resolution sports photography cameras, and an additional 6 wider-angle cameras. In about 1 second, as he holds his presidential pose, he will be illuminated by 10 different lighting conditions, which will change the polarization of the light.
All right, so this is exactly this is a combination of photometric stereo, of course, and with multi-view stereo as well, right? It's more advanced, but the fundamental principle is the same, right? By creating multiple lighting conditions and observe, like for every camera viewpoint, from the multiple lighting condition, you know the camera lighting directions, and therefore you can recover a lot of detailed information from that viewpoint. And that will give you the 3D shape and surface normal like this. Okay. So there are a lot of things you can do by just looking at the single pixel, how basically relate the intensity with the physical property. And from the multiple observations, for example, lighting directions, you can recover that physical property. Okay. All right. Sorry, I moved too fast. Any questions about this? Yes.
You don't do it by hand, so if it's like something you just like easily put into like one or so like
Yeah.
really like expensive.
Right. So imagine that in this application, you take I have a camera that's fixed. Like I have a tripod here, and you come here and you take multiple pictures. Of course, in this case, I need to know the lighting directions. So I set up like this direction. I know where the light source directions is, and I take 3 pictures, and I just need to take these 3 pictures into the code, and they will recover the 3D geometry. Yes.
You said the light sources can't be on the same plane.
Yeah, they cannot be on the same plane. The reason is because remember that we are solving a linear system equation. The light directions is the 3 rows. If they are on the same plane, which means that which means that they are linearly dependent. Basically, the third light source can be the light direction can be combined by the two linearly combined by the first two. That means there's some terminology here, like basically means that matrix cannot be inverted because they have a null space. Right? Yes.
When you set up your light sources, like how do you know what that how that will be represented as a vector? Like, is it like X, Y, Z like in space? Like
Right. So it's basically kind of imagine that you need to define a world coordinate point. For example, my the object is at the center, and then light source is this direction, this direction, this direction, and you know exactly what that direction is because you set it up. Yes.
Is there a way to kind of calculate what the right amount of like pictures that you need to take is? Just taking too many or too little?
In general, it's in this case like the more the better. Because the more like inevitably you will when you capture this you have noise, right? So if you have multiple observation, then you can get less noise. So that's why kind of in this case they captured kind of 10 different observations. Oh, sorry, they have some trade-off, right? First, the object need to be still. Like if the object is moving, then you cannot this fundamental assumption that the pixel is the same across all the illumination is not valid, right? So you have to be still. So you need to hold their breath. So that's why they only use 10 different lighting variations. But if you are capturing something that's a static objects, then you can take whatever as many as you want. Okay, the more the better, right? Because you have more observation, you get more and more accurate.
So is there like a ceiling to when taking like say instead of taking 50, take 200 photos and just increasing the cost?
Yeah. So this is a trade-off, right? So you will increase the cost. You need more storage. You need it's a trade-off. But typically you want to determine, especially when people are trying to work on this digital, like maybe there's some ancient artifacts you want to preserve. Like a lot of museums try to kind of preserve digital preservations, and they want to do this type of technology. Like basically they just use pictures to recover the 3D structures. And that there's some time constraint, right? You don't want to take 1,000 photos just for that. Yes. Right. So you can. So basically, the idea is this, right? So what you recover is the surface normal, and what I didn't talk about because this kind of what I didn't talk about this tells you for every location what is the orientation of that surface, right? And in order to get this, what you need to do is to integrate this surface normal, right? So the surface normal is the derivative of this guy. So once you have this guy, you can take the integrations of the surface normal, then you get to recover the 3D shape. Okay. Right, but you typically this was already all the 3D information is already here. Okay, so there are a lot of different light refraction models. So far we only talk about very simple one, right? We talk about the planar kind of mirror refractions and kind of specular refraction that's kind of shining surface, and diffuse refraction that's a non-Gaussian surface. There are many other things that can be quite complex, and that's why the computer graphics is very hard. Okay, so there's transparency, like the light kind of goes straight through. If a glass of water, you have refractions, like the light bend when they encounter different medium. You have fluorescence refractions. That is, the light wave come inside and the light wave comes out is different. Like that's where you get a kind of very kind of weird colors. And you have subsurface scattering. That is, if you kind of hold hold your if you have a sunny day, if you hold your fingers toward the sun, you'll see this kind of grow. And this is what happens here is that the light comes into your skin and they will scatter around and then before they bounce out. Okay, and so this is very complex phenomenon. It's not just directly bounce off the surface. Yes, sorry. Top right one is the fluorescence. That is there's some chemical, for example, some bugs that will emit light. Or these kind of some chemical material where your incident light will come from a different from specific light wave. For example, they're white color, but their reflected light will change their frequency. So that's why you see these kind of weird colors. Yes. It's not different thing. Prism basically decompose the white light into a kind of rainbow color. That decompose these things into different wavelengths. What this says is that if you shine some specific wavelengths, and the output wavelengths will be different. Okay, you will change the wavelengths of that. So it's become complicated refraction models. Okay. All right. So in general, so this is no longer computer vision. Yes, sorry.
How prevalent is luminescence? Like the thing you're taking a photograph of emitting its own light.
That become very complex, right? So in general, you have to you have a more general form. Though this kind of refraction model cannot be modeled by just like a beamform model or or an inversion, right? Those are kind of simplified assumptions about how light bounces off surface. In general, it could be very, very complex. And the most general form looks like this, okay? So you have a 3D point at the 3D surface and a point at that 3D surface, and you can see that you have a surface normal, and you have a light source. Like you have light source like at this location. Let's talk about just single light source. By the way, this is already more computer graphics, but I think it's good to understand this a little bit. So what you do is that you have this, and you have a surface. You have light source bounce off this 3D surface, and you will some of them they will be received by the observer, right? So you have an observer viewing directions, and the most general form of this is called bidirectional refraction distribution function. Okay, it's a fancy name. What does it says is that it's completely characterized how different light, if I have different light directions and a different observation, what the observation is. Okay, it's a function, it's a 4-dimensional function that looks like this. Okay, so you can characterize this by saying the following. Okay, the light output, what your output you receive at a specific angle is a function of this BRDF. Like basically, it's characterized how the surface, if I have a specific light from this direction, and how would they bounce the other directions. And the lambda is the kind of the color of the light. So you have this input. So this is the input light source, and this basically tells you how the characterized behavior of that surface point. Okay. And then you need to account for the foreshortening effect. That is, if a light source and the surface normal are oriented at this angle, then you'll receive less light. So you capture this foreshortening effects. And what you need to do is to further do more, you need to integrate all the light sources that are coming from that surface, right? If I have a surface here, when I observe this location, what I need to do is that I need to compute that response, but integrated over all the light source, that's all the hemisphere coming from right at the point. Okay, this is why computer graphics are hard, right? So you need to do this in order to capture the realistic appearance. Okay, yes. Okay, can you say it louder? Yeah, so imagine that I want to kind of characterize how this pixel the appearance of this pixel, the intensity of this pixel. What I need to do is that for any specific light source, like that light bounced off this location, observed by this. That's called BIBF. But in order to really determine this pixel not just have that light source, right? It has many, many different light sources. So you need to integrate all the light source directions from all the hemisphere. Does this make sense? Yeah. So that's why you have this integral here. To make things more complicated, you have you also could have emitting light, right? The light source may that location could also be emitting light, so that becomes complicated. Okay, this is why a lot of rendering engine need to run like a very slow. Okay, so kind of rendering realistic thing is not easy. Okay. All right. And also to make things more complex, typically if you want to build a streak like this, you cannot just model this direct lighting, right? The light source, and then you bounce off the surface and just capture this. It's not enough. What you need to do is to also account for the indirect lighting, like the light source can't bounce the surface, they will bounce to other surface and bounce another multiple times. Okay, so you need to model this kind of indirect lighting to make things more realistic. Okay, does it make sense? So this is a little bit about graphics, but it's good to understand how lights interact with the surface, and then we will talk about the other parts. Okay, so now so far what we talk about is that how light bounce on surface. The gist is that you have multiple different refraction model, right? You starting from a simple one, just the mirror refraction, specular refraction, and non-Gaussian refraction. And from that knowledge, we can build application directly using that knowledge to recover the three-dimensional shape. Okay, so it's already pretty interesting. All right, so now we need to understand how these things get measured by the camera. Okay, so if I have an observation and get this pixel, and that's actually is a fairly convoluted, this imaging system is actually a very complicated pipeline. So the pipeline looks like this. So you start from the scene, and then that has a specific energy that's called radiance, and that radiance gets to the goes through the lens, and you have an aperture and a shutter that control how much light it gets in, and then you'll hit the sensor, and the sensor will activate, converting how much photon into a voltage, and then you will get convert into the analog signal into digital signal, and you save it as a raw file. And once you have that, you'll do a lot of other processing to get to the final JPEG you see. Okay, they'll do the compressions. So this is so we will talk about more about this light, the physics of light when we talk about in the third module. But right now we stay with 2D. Okay, so this part usually can be described by can be kind of compressed, and it describes this is just a nonlinear function between the input intensity, light intensity, and the output pixel intensity. Okay, so most of the cameras, they will have this that's called camera response curve, or people call it gamma corrections. All right, so if you purchase a display, they will tell you like what the gamma correction is. So the camera correction basically it looks like this. So you have some input values, that is kind of the intensity of the light. Okay, and what you want is to have this red curve. The red curve, basically, what it does is that because we human are quite sensitive to the light that's dimmer, so want to represent that dimmer region more. Okay, so what does this function do? This function is basically if the input value is small, they stretch that dynamic range of that input range, right? You can see for between the 0 and 0.2, this range, the light is kind of darker, right? Darker area, the intensity is small. but it gets stretched into 0 to around 0.5. Okay, so you use more bits to represent that small range. Okay, that way you will be more kind of efficient in terms of how you encode the light. Okay. All right, but many of these camera manufacturers, they have a different because they want to capture different field, so they have a very different they could have a very different camera response. Okay, they have a different camera response like this. Okay, so why do we care about this? One application that sits inside everyone's cell phone. Okay, that is called HDR. So how we can do this? Okay, so the idea is very simple. You have a scene that has both dark region and bright regions, and because whenever you capture a photo, you cannot capture all the dynamic range, right? If you capture a darker region, if you take a longer exposure, then your bright region you get overexposed, and the dark region you get details. Okay, if you capture short exposure, what will happen is that the dark regions get too much. You don't get enough light, and therefore you get noisy, and the brighter region is good. So the idea is that can I capture 3 photos and combine HDR? If you have a form and whenever you capture a photo, what under the hood is doing is to capture a burst of multiple photos. Each one of them is different exposure time, and they will merge them. If you use iPhone, you have a HDR icon. They will merge them into a high dynamic range photo, so that capture all the details. Okay, so we're using the remaining 10 minutes to go through how this HDR works. Like you will find that most of the computer vision algorithm looks the same. Basically, you have a physical model about what you observe and what you don't know, and then you can set up a linear system equation to solve it. All right, so let's do this. All right, so imagine that this is the process. Like imagine that you can capture the same photo, but you capture this at different stops, basically different duration, like shuttle speed. Okay, so if you capture this, it's very dark, but these are properly exposed, right? It's good. And if you increase the stop, like this guy, okay, now this part is probably a little bit too dark, too bright, so it starts to overexpose. And then you capture this. Now you can see the dark regions. It's good, but some parts get overexposed because the dynamic range, the maximal brightest part of the scene and the darkest part of the scene is too much for your camera to capture. So you capture different shuttle speed to capture different sections. But the question is how you can recover based on that partial observation from multiple exposure time, how can you recover the actual radiance? Okay, so the idea is that I want to get these 4 photographs based on these observations. How can I recover this? Okay, so this photo has everything we want. We want to have properly exposed bright regions, and also the dark region is also the details are captured. All right, so this is called high dynamic range imaging. All right, questions so far? No? Yes.
Do they also do this with video?
Yeah. They are like videos become more complex because you have moving objects. So they are high dynamic range videos. So what you need to do is to be able to track you still have the kind of interleave, like, for example, different exposure time, and then you can once you can compensate the motion, you can still recover the high dynamic range. Okay, so let's see about images. Like right now, we assume that everything is static. So here you have 4 images. Okay, so I1, I2, I3, I4. Right. So what you have is that let's call a particular pixel. Again, this is just a pixel-based algorithm. Like for every pixel. Okay. You have a pixel I1. This is ith pixel captured by the first camera, the second camera, third camera, and fourth camera. All right. Each camera basically means that you capture at different exposure time. Okay. So the exposure time is basically how much light you observe per time, but you integrate that over time, right? You have an exposure, you have a shutter open and to close. That's your exposure time. So that's your energy you receive, actual total energy you receive from that. So you have basically your radiance and integrate over time. Okay, so you have different time interval. That's how much exposure time you capture for each photo. Right, on the left hand side it's very short. On the right hand side it's longer. Okay, so what do I want is that now this intensity you observe is some kind of function of this exposure time of this energy. Okay, so this is a relationship. Okay, and you can see this is basically just the radiance of that pixel times the intensity. And this guy is a nonlinear function. All right, so let's try to massage this equation a little bit. So this is the pixel value. Again, there's the purple one is a function, it's a camera response function, and I have a radiance and an exposure time. Okay. So what we could do first is that I can move this around because I don't want to model the forward. I want to model this inverse of this response curve. And because these things are multiplied together, this is kind of a bit messy. I can apply a log. And the log doesn't change anything. I just operate things in the log space. So now I have these two things separated. Okay, so let's give this f of inverse a name called g. It's just a function that if I give you different intensity value, I'll give you different radiance. Okay. So now I have an equation, right? Similar to before, I have an equation, a single equation. Now later on, what we need to do is that I just want to find the unknowns such that I can minimize the overall arrows, right? These are the arrows, and I want to integrate for every pixel for every photos, right? So this I is the number of pixels, J is the number of pictures, right? I basically need to minimize these things, okay? And then for some intensity value, if it's overexposed, then I don't trust it, right? So they have some weighting function here, but we can have some weighting function here, and we have some regularizations. Okay, so we'll talk about this later. So now the things what we do know is the weighting function we know, the exposure time we set is ourselves, like how much time we expose, and what we don't know is this two. Okay, so now how can we solve this? Now let's do the kind of this linear system. How can we solve this with the setting up linear system equations? So now let's kind of shuffle this around. Again, this is the same equation. Basically, for every pixel, I will be able to see, I want to know the G and R. Okay, so this is the linear system equations. So how do I solve this? Okay, so let's walk through a toy example. Let's say that the Z in practice, they have 0 to 255. Okay, so they have 256 possible values. But let's say my camera can only capture 4 types of values. Okay, for 0, 1, 2, 3, these 4 bits, like 2 bits only instead of 8 bits. And then I capture 3 photos, 3 exposures, and I only have 2 pixels. Okay, so simple toy examples. Okay, so now how can I do this? Right. So again, let me simplify this. So, and I assume that the data I capture is that the intensity for pixel 1 at the exposure 1 is 0, at exposure 2 is 1, exposure 3 is 2, and the second pixel is 1, 2, and 3. So it's basically made up of some numbers. Okay. So what does that look like? So you can look at this basically unknown, unknown, and known. What are the unknown? Let's put this unknown into a vector. Okay, these are the unknowns. I want to know what the function g is. What is, because I have 4 possible numbers. So I have g0, g1, g2, g3. These are unknown numbers. And log r1, log r2, these are unknown number as well. I want to figure out what this does is that I want to figure out how the camera converts the radiance into pixel values. And I also want to know what's the dynamic range of these 2 pixels. This is R1, R2. Okay, so these are unknown vectors. So now, based on that observation, let's set up a linear system equation. Okay, so it looks like this. So I want to basically fill this in the form of ax equal b, and then I can solve this with linear square, right? So let's first look at the first pixel and the first observations. So if you look at this equation, you can rewrite that equation into a matrix form like this, right? So what this does is that the 1 times g0 basically says the first one, the first pixel observed by the first camera is this guy, minus the r log r1 here, this multiply this equals this guy. Okay, that's the first pixel captured by the first camera. Okay, now you have a linear system of equation here. Okay, and the first pixel captured by the second camera, you can write down this guy. Like the second pixel is these values, so g1 minus this guy minus log r1 equals to this one. All right, the same pixel captured by the third camera, you can write this down. Like every equation, you can fill that rows into these things. Okay, you can fill this row. This is the second pixel captured by different camera. Then you can fill this up. Once you fill this up, you have a linear system equation. Then you can solve for this guy. Okay, make sense? This simple algorithm is embedded in 1997, and I'm pretty sure that all your like iPhone or cell phone, when you press a shutter, then compose the linear HDR, this running a variant of this. Okay, so it's really simple, right? Every pixel, you just capture these things and then set out the linear system equations. You can solve for the camera response curve as well as the radiance of that. Okay. All right. So I'll stop here. I will complete the color part, and I will move on to the filtering. All right. Thanks.